All right, so our second experience here today is we're looking at another way of using experimental data to do something. And in this case, we're looking at integrated rate loss. So what is the difference between a method of initial rates and an integrated rate law? Well, the main difference is this. With an integrated rate law, what we are doing is we are isolating one of the reactants and using that reactant to determine what its order is based on how it changes over time. And so this is a graphical kind of interpretation where we're going to do graphing and graphical analysis. If you've got your laptop and you have the ability to open up either Sheets or Excel, I'd go ahead and do so because that is something that we're going to model and do together. But what we're looking for here is, again, we're not getting all of the information. We're not going to be measuring the instantaneous rates and the initial rates and looking at how things change as we manipulate variables. We tend to do this particular technique when a reaction is usually longer. So the reaction that we're going to explore on Monday that does this, we're going to look at a purple dye called crystal violet, and we are going to basically decolorize that dye. And the process of decolorizing it actually takes, depending upon the concentrations that we use, up to about 30 minutes to do. So rather than set that reaction up and do it 10 different times to figure out all the different orders and things, what we're going to do is we're going to use this method of integrated rates, monitor the concentration of the crystal violet using a spectrophotometer, and then graph it and figure out what its order is based on the type of graph it makes. And what we're ultimately looking for here is linearity. That's the integrated part of the integrated rate law. We're looking for linearity. What kind of graph relationship gives me a straight line to interpret? And why do I want a straight line? Because straight lines are incredibly easy to interpret. You know slope-intercept form, y is equal to mx plus b. Linear graphs give us a slope-intercept equation that we can use to manipulate, modify, and use to determine things. And so we want to illustrate that here. So for a zero order reaction, we know that from a rate law standpoint, the rate of the reaction is just equal to the value of the rate constant. But from a graphing standpoint, what we're going to do is we are going to graph the concentration of the reactant A over time. And when we do that, the resulting graph is going to give us a line where the slope of that line is equal to the opposite of the rate constant K. And the intercept of that line, where time is equal to 0, is going to be the starting concentration, A naught, so to speak, where time is equal to 0. And what we'll see is that as we go through and look at these different reaction orders, we're going to have roughly the same interpretation each time. Each one of these graphs is going to generate for us a straight line. or at least what we hope is a straight line. But the interpretation of what y and x and b mean is going to change. X is always going to be the time. But is our y going to be simply the concentration, like it is in zero order? Or is it going to be a manipulated function of that concentration? Well, for first order, it's a manipulated function. It's the natural log. For second order, it's a manipulated function. It's the reciprocal. We also want to look at, well, what does the slope of that line tell us? Well, for zero order and first order, the slopes are going to be negative. We know that the rate constant can't be negative. So the rate constant must be just simply the opposite of that slope. The second order plot, because we've taken the reciprocal, that means that instead of decreasing over time, y is going to increase over time because it's 1 over a. We're going to get a positive slope graph, so we don't need to manipulate the rate constant for that one. So in total, we're looking at 3 different graphs. And we are manipulating those variables, concentration and time, specifically concentration, in a couple of different ways to see where it fits and where it fits best. And so all of that graphing that you did in Chem 105 in lab, that graphing skill that you had to learn to be successful in that class, it comes back here again. Because the way to do this, to figure out which one is the correct order, comes down to linearity. Does anybody remember how we determine linearity when it comes to a graph? Whenever we graph, we always toggle a couple of options, right? We want the equation of the line, and we always want that one other thing. What is that one other thing? R squared. Okay, R squared is your linearity. Remember, R squared is a calculation of how well does the line, the trend line, fit your data. And the closer it is to 1, the better the line fits the data. And so what we'll do is we'll end up taking our experimental data and making 3 different graphs. A graph for zero order, a graph for first order, and a graph for second order. And from those data and from those graphs, we're going to look at R squared. And whichever one has the data that fits the best, that's going to tell us what the order is. Now, sometimes that's going to be blatantly obvious. You know, if the proper graph is a natural log, the zero order plot's going to look pretty horrendous. Let's skip this for a second. Let's go into the guided example. Because I think you'll connect the dots a little bit better once you see kind of what it is that we have to do. So here we are studying the kinetics of the decomposition of dinitrogen pentoxide. Now, there is a claim that the decomposition here is first order. We are to test the validity of that claim and also determine the value of the rate constant itself. And so what we need to do is we need to open us up a copy of Excel or Sheets, whichever one you're more comfortable with. And we need to import this table. And so if you don't have the PowerPoint and the Excel open at the same time, that's okay. I'll give you a minute here to copy everything in. But just give me a little indication some kind of way if you're ready. Now, ultimately here, we're going to have to make 3 graphs. So once you've got the data in, what I would do is I would copy and paste the time column to make the creation of the second and third graph a little bit easier. Now, we're not going to keep these numbers, but just to keep the headings pretty here. This one is going to become the natural log of that concentration. And this one is going to become 1 over the concentration. And so if you don't remember how to do calculations in Excel, just remember it's equals. And then we type in the function. So natural log would be ln, parentheses. And then instead of inputting the number, which would basically be calculating it by hand, we're going to select that cell. And then we can repeat that by copying and pasting the formula over the rest. And then for the reciprocal, same thing, equals 1 divided by the original concentration, and then copy and paste to get the rest of it. All right, so we've got our data now. We need to make our 3 graphs. So hopefully you remember how to do this from lab. We're going to go to Insert Charts. We want a scatter plot. We can worry about filling in the gaps here at another point. But right away you can see pretty clearly this is not a linear plot for 0 order. Look at how it is curving and tailing there at the end. For completeness here, we'll go ahead and we'll add in the titles, we'll add in the trend line. We'll make sure that we go to more options here and put in the R squared and the equation of the line. But we can see pretty clearly here at 0.8871 for R squared, this is not a very linear fit. So 0 order is probably not the correct answer. So let's move on to first order. We're going to do the same thing. Insert chart, scatter plot. We can see here, it's pretty linear. Let's go ahead and add all of our stuff to it. Get the R squared and the equation. And not only is it good, it's perfect. This plot is perfectly linear. So the original claim that this was a first order reaction seems to hold up pretty well. We've got something that's perfectly linear here. Now, just for the sake of completeness, let's go ahead and do the second order plot just to kind of verify. And we can see that, I mean, it is curving. So it's really not that much better than the first plot was. So first order, or I'm sorry, 0 order. 0 order is actually better than second order, which is kind of unusual. But neither of them are good. They're both bad. So with the graphing here, we have been able to determine the first order status for dinitrogen pentoxide. We've done that. Now, the second question is, what is the value of the rate constant? For that, we need the slope of the line. Now, here's one place where we do want to kind of make sure that we're being careful. Now, it doesn't look like that we were terribly worried about sig figs in our plot here. Looks like they're generally going off of 3. So since our rate constant does not have 3 in it, because we're going to want to set that up. So all we did was we just manipulated the numbers here in the text box to give us that third significant figure. The rate constant is the opposite of the slope. So the slope was negative 0.00693. That means that the rate constant would be positive 0.00693. And the unit there, since it is first order, would be reciprocal seconds. So how do we test the validity? We did the graphing. The graphing validated that the first order plot was the most linear. Value of the rate constant is equal to the opposite of the slope. So 0.00693, and the unit would be reciprocal seconds because it's a first order. Like I told you last hour, we can always tell the order of the reaction based upon the unit of the rate constant. First order rate constants are going to have reciprocal seconds as their order. It's all about how it multiplies out, divides out in that process to give us molar per second. So now that we've seen it in action, let's go ahead and try to answer some questions about it. Kinetic data for the reaction from A to B gives a straight line when a 1 over A versus time is plotted. The initial concentration of A was 2 times 10 to the negative third molar. The slope of the line is 2.5 times 10 to the negative second per molar per second. What is the order of this reaction? So there are 2 pieces of data that we look at that would give us the answer here. The first thing that we're told is that the plot is 1 over A versus time. Well, 1 over A versus time, that is, definitionally speaking, that's a second order plot. So that was our first clue that this was second order. The second clue was that They give us the slope of the line, and the unit on that slope per molar per second. Well, that's a second order rate constant. So either of those pieces of information would have been sufficient for you to understand and to know that this was a second order reaction. Questions here with that? Okay. The last bit of information that we want to go through today and for this week is the concept of a half-life. Now, half-life for reactions kind of gets brought up in a number of different ways. We hear it used in different kinds of contexts. In particular, the definition, anytime we're talking about anything chemical related, whether it's the half-life of a drug or the half-life of a radioactive material, they all should tell us the same thing. A half-life is how long does it take for the reaction to get halfway to completion. So if I am starting with X amount of reactant, how long does it get to 1/2 of X? And the integrated rate law provides for us, because we have an equation to work off of, the integrated rate law provides for us a way to calculate half-lives and use half-lives to actually help us to calculate rate constants. Because what we can do is we can manipulate that integrated rate law accordingly. So let's take zero order, for example. There's my integrated rate law for zero order. Now, at half-life, my concentration of A is equal to half of my initial concentration. So if I substitute that, I can do a little bit of algebra here, and I subtract A from both sides. I end up with negative 1/2 A is equal to negative K times T 1/2. If I divide each side by negative K, I end up with this equation here, where the half-life is equal to the initial concentration divided by 2 times the rate constant. And so for zero order reactions, the half-life ultimately depends on how fast the reaction goes in general, but also how much starting material you have. The more starting material you have, the longer the half-life is going to be. Now, you can do this relatively simple substitution and manipulation for all three of those half-life equations. And when you do so, what you'll see is that for first order is actually the only one where the value of the half-life has nothing to do with the concentration. Doesn't matter how much I start with, the half-life is exactly the same. Where this is in particular really useful is for things like radiometric dating. If you've heard of carbon dating or any other kind of isotopic dating, one of the reasons it's a reliable method is because I don't need to know how much carbon was in the initial sample. I just need to know I need to know a rough comparison of how much the relative ratios are, because the half-life is the same regardless. So if I can figure out how many half-lives have passed, I can figure out how old the object is. And the way that they do that is they look at, okay, they look at something called carbon 14. Carbon 14 is the radioactive isotope of carbon. It's present in less than 1% of all carbon samples. But we know that, for example, human beings or any other living thing that is carbon-based, because we eat and sleep and regenerate and metabolize, the amount of carbon 14 in our system is constant because we're constantly regenerating and taking in new sources of carbon. When we die, we're no longer taking in new sources of carbon. And so the carbon 14 concentration in our body changes as we change. And so they can take a look at, okay, living human beings should be about 1% carbon 14. How much carbon 14 is in that thing? And they can compare the two and get an idea about how old it is. Half-life for carbon 14 is somewhere just around 5,700 years. Now for second order reactions, again, we can see that not only is there a reference to the rate constant K, like there is in all of them, but again, A is a factor as well. And it's also an inverse factor. The higher the concentration of A, the faster the half-life is going to be. It's going to take less time. And so kind of putting all of this together here, integrated rate laws are useful in situations where running multiple reaction runs is either not feasible or improper, it takes too long. But by manipulating that variable and by comparing things justly, what we can get is we can look at the graphs and we can determine the order of the reaction based off of that data. And because we have that information, we can also derive information about half-life, get an idea of how long it takes for half of the reaction to go. Let's take a look at a practice problem here. And then I've got one more for us to try together, and then we're going to call it a week. So we've got the decomposition of N2O5. We are told that it is first order in dinitrogen pentoxide, and that its rate constant is 0.00693, which, oddly enough, that sounds familiar because it's the exact same reaction that we studied when we did the graphing. Initial concentration is 0.375. Question is this: what is the concentration after 3 minutes? Second question: how long does it take in minutes for 95% of it to decompose? So for all of those questions, if I have the graph, I could just throw it up into the graph. But if I don't, that's okay too, because I've got the integrated rate law. And since it's first order, I know that it's going to be the natural log of N2O5 is equal to negative K times T plus the natural log of the initial concentration. Well, I got all of that information. I just need to figure out how to use it. So for question number 1, I want to know the concentration after 3 minutes. Well, my rate constant is in seconds, reciprocal seconds. So I need to turn this into seconds first. 60 seconds in a minute. We've got 180 seconds. So I'm going to set it up. Natural log of the concentration is equal to negative K 0.00693 reciprocal seconds times the time, 180 seconds, plus the natural log of the initial concentration, which is 0.375 molar. I've got all the data I need. I just need to compute it. 0.00693 times 180 is negative 1.25 plus the natural log of 0.375 is negative 0.981. So I put those two together, and I've got negative 2.23. How do I get rid of a natural log? Yeah, you raise it as the exponent to e. So e to the natural log cancels out. E to the 2.23, negative 2.23 rather, to 3 significant figures is 0.107. Okay, so that's the first one. For the second one, we're looking for 95% decomposition. So that means that only 5% is left. 5% of 0.375 is 0.0188 molar. Setting up the exact same way. This time I'm solving for time instead of concentration. So natural log of 0.0188 is equal to negative 0.00693 reciprocal seconds times time plus the natural log of 0.375. Natural log of 0.0188 is negative 3.974. Natural log of 0.375, we already did. It was negative 0.981. So we've got to do a little bit more algebra here. Add 0.981 to each side. and then divide. Our answer is going to be in seconds because our unit is in seconds. It's going to be 432. And then divide that by 60 for minutes. You get 7.20 minutes. So using integrated rate law is not always all about the graphing. Sometimes we just need to use the result of that to use that equation to figure out whatever information is missing or to help us predict, okay, how long does it take for this to happen? Or what's going to be the concentration after this amount of time? We're even working backwards. How much did I start with if this much is left after this amount of time? And we can do all of that with these equations. It's just a matter of algebraic manipulation. All right, last question for the week. We were given data about this particular reaction in an earlier problem. It's the same information, initial concentration and slope of the line for a second order reaction. The question is this: what is the half-life in seconds? And what we want to set up is, since this is second order, we are going off of this second order integrated rate law, which is this. Now, you could scroll back to this slide and say, okay, the equation tells me that the half-life of this reaction is equal to 1 over K times the initial concentration. You could do that. But let's say that you forgot that that existed. You don't need to worry about it. You don't need to memorize that extra equation, because since it's a half-life, we know what that concentration is. It's half of this one. So I can just plug it in here, 1 times 10 to the negative third, because that's half of the initial. And the slope of the line is our K, 4.5 times 10 to the negative second per molar per second. So I can start working out the math here. 1 divided by, well, that's 1,000. One over 2 times 10 to the negative third is 500. So 1,000 minus 500 is 500 is equal to that. And so I could solve by just doing my simple algebra here. 500 divided by 4.5 times 10 to the negative second to two significant figures, 11,000 seconds. All right, any questions with that one? All right, so this is where we're going to call it for the week. On Monday, we are going to talk about two different things. First thing that we're going to talk about are reaction mechanisms. So how do we kind of contextualize the rate laws that we've been spending today calculating and talking about in terms of what actually happens at the molecular level when these things react? So that'll be the first thing that we talk about. The second thing that we'll talk about is we'll kind of circle back to the idea of what causes reactions to go faster, and we'll talk about catalysis and some of those other factors like temperature that we haven't really discussed yet, but we need to come back to. So we'll close it up right there. And for those of you that are